So the last 2-ish weeks, we've been working on work energy theorem, okay? In work energy theorem, okay, energy, mechanical energy, changes. We only had to do problems where either potential energy or kinetic energy changed, okay? But still, the mechanical energy changes if either one of those energy types changes. Okay, everybody with me on that? Okay, work is a change in mechanical energy. Work energy theorems generally have as givens, okay, and as context, a force being exerted on something through a distance, and then either the speed of an object is changing or the height of the object is changing. Would you agree with that statement? Okay. The kinds of questions we're going to work on today are a little different. Algebraically, they're very much alike. You're going to have to set things up. This is equal to that, move things around. That part I have full confidence in your ability to do. The context of these questions is a little bit different. Okay, so let me ask you this. If work is a change in energy, that means that work equals the final energy minus the initial energy. Right? That's what we've been working on the last few weeks. What if there's no work done? What if work is 0? What does that say about these two numbers? They're equal. They may both well be 0. Who knows? But either way, they're equal. Okay? If I was to manipulate this equation for EF, right, what would I do with EI? I would add it to the other side, right? So if I add EI over here, I have EI plus 0 equals EF. Well, that means EI equals EF mathematically. So in any situation where no work is done, energy is conserved, okay? I want to follow my wording on that. Okay, conserve means to keep it the same. All right, all of it is accounted for. So in a law of conservation of energy question, no work is being done, which means you won't get force, you won't get distance, and both velocity and height will change. Okay, you'll actually get both in these kinds of questions. The reason I'm telling you that, I want you to be able to tell them apart. Okay? Because a lot of times when you read them, they can sound a lot alike. They give you a lot of the same givens, okay? And it's easy to get them confused. The way you tell them apart is this. If the question gives you force, it's a work energy theorem question, okay? Automatically. You will never be given force in a question where energy is conserved, because forces change energy, okay? If both the height and the speed are changing, if you're given both in a question, it's a conservation of energy question. You're never asked to do a work energy theorem question where both of those things change. Okay? This is kind of how you can tell them apart. Okay, so as a quick review here, okay, we have to remember what mechanical energy is. Mechanical energy is the sum total of the object's potential energy and its kinetic energy. It's possible for something to have both. Okay? A plane flying through the air, okay, has kinetic energy because it's flying forward, and it has potential energy because it's above the ground. Right? So it has both types. It has mechanical energy. Everybody all right with that idea? Okay? Is it pretty easy to calculate those two things? Right? We have a formula for each one, right? We have a formula for potential and we have a formula for kinetic. Okay? So it would be pretty easy to calculate an object's mechanical energy, provided we had its mass, its speed, and its height. And if we had those things, we could calculate its total mechanical energy. All right. So here would be an example of that. Okay? I've got a baseball, and it's thrown in a straight line through the air. Okay? I know its mass is 0.3 kilograms. I know its height is 2.5 meters. And I know its speed is 20 meters per second. Okay, so I'm given that it has kinetic energy, it has potential energy, and has mass. That's kind of important. Okay, so I'm going to calculate its mechanical energy. I'm just going to plug in Okay, those two formulas, I know how to solve for kinetic, I know how to solve for potential. I just plug in my numbers. 1/2 times 0.3 times 20 squared gives me and then add the potential, 0.3 times 9.81 times 2.5. And we find that this baseball has lots of kinetic energy, not very much potential. Why? How high is 2.5 meters? Maybe about that high. Okay, is that very high? It's not very high off the ground, so it doesn't have a lot of potential energy, plus it doesn't have a lot of mass. It has a fair amount of kinetic energy though, because it's moving pretty fast. 20 meters per second is pretty fast. Okay, so I take its kinetic energy, I add its potential energy, here is its total mechanical energy. Okay, fairly simple calculation. Really just plugging in numbers here, right? Okay. I would like you guys to try, let's say just for right now, question 8.
You have to change the mass into kilograms.
Exactly. Got to put mass in kilograms. They give it to you in grams. Dirty trick, happens all the time. Okay, we got to recognize that a joule is a kilogram meter per second, meter squared per second squared. Okay, that's the importance of knowing those fundamental units. Okay, knowing that this has to be in kilograms. So if we are looking at solving that one, okay, we would have mass 0.300 kilograms, because there's 1,000 grams in a kilogram. Okay, we're told that it is moving at 8 meters per second, so we have V. And we're told it's 30 meters. Yeah, 30 meters above the ground. All right, so then we want to calculate its mechanical energy. That's going to be potential energy plus kinetic energy. And then we just put in the formulas. We don't have to manipulate anything here. We just have to plug numbers in. Okay, the mass is 0.300 times 9.81 times 30 meters. Okay, we're with me so far. And then add on to that, okay, 1/2 times 0.3 times 8 squared. Right, that should give us 97.89 joules, okay, worth of mechanical energy. Okay, everybody all right with that? All right, the next two, still the same formula, but the next two are going to ask you for either the potential or the kinetic. Okay? Doesn't really change much, except you'll be given this number instead. Now, a quick reminder here, because of the way they give these numbers here. Okay, you can see that they give the mechanical energy in both of these questions in scientific notation. Okay, so if I get a number like this, 3.00 times 10 to the 3, okay, I've got to either punch it into my calculator that way as 3E3, okay, or I just convert it back out to normal. Okay, 3 times 10 to the 3 is how much? 3,000. 10 times 10 is 100 times 10 is 1,000. Okay, so that's really all you have to do. It's not terribly difficult, right? You can also just do this. Whatever that number is, move the decimal that many places. Okay, put in zeros if you got empty cups. Okay, so you put in the 0 there. If it's 10 to the minus 3, then you go the other way. Right, so doing scientific notation, hey, we kind of expect you guys already know how to do that at this point, so we don't spend a lot of time going over how it works. Okay, all right, give you a few minutes on 9 and 10 there. Okay, so we have a construction worker who drops a 2 kilogram hammer from the roof. Okay, when the hammer is 50 meters above the ground, so they've given us two things already. They've given us the mass, okay, and it's 2 kilograms. And they've given us the height, 50 meters. Okay, when the hammer is 50 meters above the ground, it has a total mechanical energy of 1,880 joules. Okay, calculate the kinetic energy of the hammer. Okay, do I have enough information to calculate the potential energy of the hammer? I do, because as far as we know, we're the only place that uses hammers. Okay, so we know that G is 9.81. Okay, they're not telling us it's a Martian hammer, okay, or anything like that. So, my mechanical energy, okay, equals my potential plus my kinetic, and I want to find the kinetic, so what do I do with the potential? Subtract it over the other side. Okay, so EM minus EP equals EK. This number is 1,880 joules, okay, minus M, 2 kilograms, times G, 9.81, times height, 50, is going to give me the kinetic energy, right? And if I plug all that in correctly, 1,880 minus 2 times 9.81 times 50, 899 joules worth of kinetic energy. Okay, now, that is not how I would ask that question. What would I ask? I'd want to know how fast the hammer is going. Can I calculate that now? I have the kinetic energy. Okay, I know that EK equals 1/2 mv squared. I know the mass. I know the kinetic energy. It's 899 joules. So I would just divide both sides by half of m and square root. We've done stuff like that in the work energy theorem questions. We know how to manipulate that formula already. Right, and then, not the formula. Okay, and then we'll have our 899 divided by 1/2 times 2, so basically the square root of 899, because half of 2 is 1. Okay, and if I do that, I should get 30 meters per second, like 29.9 or something like that. 30 meters per second. Okay, is that a big leap? Not really. Okay, and that's the kind of thing we're going to be doing before the end of class today. All right, quick review here. We've done so many bow and arrow questions, we should be getting sick of them by now. So I use 100 newtons worth of force to pull a bow back, 1/2 meter. How much work have I done? $50 joules. How'd you do that? Right. We did this. Work equals force times distance. 100 newtons times 1/2 of a meter. That's 50 joules. That's the work energy theorem part of this question. The rest of this question is conservation of energy. Law of conservation of energy says that once energy is in a system, it must be conserved. Okay? That is, it has to be in that system, always, unless that system does work on something else. This isn't talking about that. So, how much potential energy is now stored in the bow? 50 joules. Not a trick question. Okay? I did work on the bow. That work has to turn into something. It is elastic potential energy in the bow. That's part of the conservation of energy part. Once you do work, that energy has to be accounted for. Now, how much kinetic energy does the arrow have the instant it's released from the bow? So I draw the bow back and then I let it go. It exerts a force on the arrow through that 1/2 meter. 50 joules. Again, the energy of the bow arrow system has to be conserved. Once the bow is released, it does work on the arrow and transfers all of its elastic potential energy to it by doing work. The energy is conserved and we still have 50 joules worth of energy. Now it's kinetic energy in the arrow. If this is shot straight up in the air, how much energy does the arrow have at its maximum height? 50. Okay? But all of it would now be potential. Because when you throw something or shoot something up into the air, when it's at its maximum height, just before it turns and falls back down to earth, how fast is it going? 0. Okay? When something goes up in the air, it goes up, 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 stops for a second, and then comes back down. okay? And when you're at your maximum height, all of your energy is potential because you're not moving for that instant in time, okay? When the arrow comes back to Earth, how much energy will it have? 50 joules, okay? It'll just all be kinetic again, okay, when it comes back to Earth. This is why, if you're in like the perfect physical world, in an isolated system, if you shoot a gun straight up in the air, don't wait. Don't stand there. Why? Will the bullet come back down? How fast will the bullet be going when it comes back down?
The same.
Same speed you shot it at. That makes it pretty dangerous. Okay? In the real world, that doesn't happen. Because in the real world, there's air resistance, friction, there's probably wind blowing it to one way or the other. Okay? But if you were in a perfect physical world, in an isolated system where there was no air resistance, no friction, okay? If you shoot that bullet straight up in the air at 800 meters per second, it's going to come back down at 800 meters per second. That makes it very dangerous. In the real world, it slows down, gets to its maximum height, which it would do in the perfect physical world as well. Okay? But when it comes back down, it tumbles because of air resistance. It tumbles over and over, and it doesn't end up being as fast when it comes back to Earth. Okay? Everybody okay with that idea? Okay? But we only deal with the perfect physical world. In the perfect physical world, that's not a good idea. Okay? All right. We already did the seagull question. Okay, so let's try this one. You guys have this one in your notes already. It's in the notes package anyway. Okay, the dropping a rock question. Okay, so in this question, I'm given the mass of the rock. Okay, and I'm told that it's dropped over the edge of a cliff. So somebody stands at the edge of a cliff holding a rock out over the edge. Okay, how fast is the rock going? 0. Okay, so when the rock is 30 meters above the lake, it's not moving. All right, so we know its initial height is 30 meters. We know its initial speed is 0 meters per second. Okay, it's at rest, right? We said this back when we were doing acceleration stuff. If something is dropped, we know its initial velocity is 0. Okay, what's the speed of the rock just before it strikes the surface of the lake? Okay, so the instant, just as it hits the surface. Okay, what's its height then? It would be 0. Okay, so its final height is 0. And we're looking for how fast it's going. Leave that question.
Can we get force from this? Like transfer kilograms into grams and then multiply it by 98.1? Because isn't that how we get to
That would get you well, actually, you wouldn't want to convert it to grams, but if you multiplied the mass times acceleration to do gravity, you would have the force of gravity, which is what's causing the change between potential and kinetic in this question. There's not really a need to do it here. Yeah. Okay, so in this question, since, am I given force or distance or anything like that in this question? Does it mention the word work? Okay, so this is not a work energy theorem question then. Okay, whatever energy the rock has when it's in the person's hand is all the energy the rock will ever have. Okay, they're not throwing it, okay, they're not exerting a force on it through a distance, they're just gonna let it go. All right, so that means that its energy here and its energy here they're the same. They're equal. It's conserved because it doesn't mention air resistance or anything like that. So then I have to assume that the energy initial and the energy final are the same number. All right, so that's where we get this idea from. I can identify that this is a conservation of energy question because no work is being done. The energy isn't changing, but the rock is going to fall. Okay? The height of the rock changes, the speed of the rock changes. When either one of those changes, okay, something's got to give, right? Like we've got energy changing. But what's happening here is one type of energy is changing into another, right? What kind of energy does the object have right here? Potential. What kind does it have here? Kinetic, right? The potential turns into the kinetic. There's no work done. There's no energy added. Energy can change without work being done as long as it changes from one type to another. Okay, everybody follow me there? Okay, and that's what's going on here. So when I write this, what I'm really saying is this. The initial potential plus the initial kinetic equals the final potential plus the final kinetic. Okay? Mechanical energy initial equals mechanical energy final. We calculate mechanical energy by adding together the kinetic and the potential. But as we just identified, some of these energies are zero in this question because of the context, because of the situation. Okay? Since the object's being dropped and its initial velocity is zero, it doesn't have any of this, does it? Right? If I put in that formula and put in 0 for V, I'm going to get 0 kinetic energy. So that's gone. Are there any other energies in that formula that are 0? Right. The final potential energy is 0 because we identified over here that its end point is the surface of the lake where there would be no height anymore. Okay, so the final height is 0. That means if I went m times g times h, I would get 0 for that. All right, so now we've got this set up that the initial potential equals the final kinetic. We're still saying the initial mechanical and the final mechanical are equal. We're just saying that initially it only had potential, and at the end it only had kinetic. Everybody okay with that? Okay, they're still equal, so no work is being done. Okay, so m times g times h initial equals 1/2 mv final squared. Have I written the same thing 3 times now? I have. I've written that the initial energy equals the final energy. I've just written it in 3 different ways. Okay. Can I now isolate how fast it's going when it hits the lake? How do I get VF by itself? We did a whole bunch like this last week, guys. How do I get VF by itself? Right. Divide 1/2 times m over here. Okay, I don't have any addition or subtraction here. Does the mass matter? Can I cancel it? I can. Okay, here's why. Does it matter whether I drop a 1.5 kilogram rock or a grand piano? Will it be going the same speed when it gets to the lake? It absolutely will. Okay? All things fall at the same rate, 9.81 meters per second. Will the grand piano have more energy? Absolutely, but it'll be going the same speed as the rock. Okay? If I drop them at the same time, they both splash into the water at exactly the same time, going exactly the same speed. I'd just rather be under the rock than the piano. Okay? All right. Now, if you're not comfortable canceling the mass, you don't have to. You were given it. You can punch it into your calculator if you want. You'll get the same answer. Okay? I'm going to leave it in there just for the sake of kind of showing it all. All right, that gets me VF squared. So I'm going to square root that just like I would have done with the work energy theorem question last week. Okay, and now I'm solving for VF. Okay, so VF is going to be 1.5 times 9.81 times 30 divided by 1/2 times 1.5. Okay, if I do that, I should get the speed of the rock when it hits the lake. All right, so 1.5 times 9.81 times 30. Okay, divide that by in brackets, 0.5 times 1.5, and then I square root that. Okay, it's going to be moving at 24.3 meters per second when it hits the lake. just to prove to you that I don't need the mass, okay, I'm gonna do this calculation with the mass canceled out. So it'll be 9.81 times 30 divided by 1/2, square root. Look at that. Didn't need the mass at all. Okay. Everybody all right with that? You can leave the mass in if you want. You can take it out if you want. Okay? It doesn't make any difference unless they say, what's the energy? Then I need mass, because obviously a grand piano has more energy than a rock. Okay? But if it asks for a speed or a height, they don't need mass for that. Okay? Because all things are affected by gravity equally. Okay, well I'm gonna give you a little, actually, sorry, let's do these two, then I'll give you a little break. Okay, so these are very similar to what we just did. Okay, number 11 is exactly like what we just did. Number 12 is slightly different. Okay, so I'm gonna give you guys a few minutes on that and then we'll go over them together. Okay, so context of the question. I'm dropping something, not throwing it. Okay, not launching it in any way. Am I doing any work in question number 11? No. There's no mention of force, okay? There's no mention of work, right? This is just something falling and thus converting its potential energy into kinetic. So I know right away that this is true from the context of the question. No work is being done, energy is being conserved, okay? Now, the things I know are that I know the mass is 10 kilograms. Okay, I know the initial height is 12 meters. I know that it's being dropped, so I know its initial speed is 0 meters per second. And they want to know the speed of this massive water balloon. Okay, 10 kilograms is 10 liters of water. Okay, like this would hurt if it hit you. It's a big water balloon. Okay. We know that we're looking for its final speed when it hits the ground. So I know that its height final is 0 meters. They always say just before it hits the ground, okay? But it's like as it hits the ground. All right. So height final is 0 meters on that one. All right. So mechanical energy initial equals mechanical energy final. So EP initial plus EK initial equals EP final plus EK final, okay? And I know that my final height is 0, so that's 0. I know my initial speed is 0, so that is 0. And I'm left with initial potential equals the final kinetic, okay? Because all that's happening is the object is falling and converting its gravitational potential energy into kinetic energy. All right, so now at this point, I can put in my formulas. M times G times H initial equals 1/2 mvf squared. Since m is in every term, okay, mathematically speaking, I can get rid of it. I don't have to, I can leave it in there, okay? But I'm looking for vf, so I'm going to divide both sides by half of m. Okay, so I'm going to cancel it off there, and then I'm going to square root that to get vf. So that'll be the square root of 9.81 times 12 meters, because I'm canceling the mass, and divided by 1/2. Okay, so 9.81 times 12 divided by 0.5, square root that, 15.3 meters per second. How many people have done number 12? Okay, I'm going to give you 2 more minutes, and then we're going to go over number 12. Okay, number 12 is slightly different, and just for context, okay, this trampoline is at ground level. Okay, so it's one of those ones where they dig a hole under the trampoline, and the trampoline is level with the ground. Okay, what does that mean for your height? Yeah, your initial height is 0 on this one. Okay, all right, I'll give you a couple more minutes on that one. All right, so on number 12, okay, 30-kilogram child on a trampoline jumps vertically into the air at an initial speed of 1.6. Calculate how high the child will rise. Okay, am I given any forces? So no work is being done here, right? Okay, so I can assume that the energy the child has when they leave the trampoline, which is like the ground, okay, will be equal to the energy they will have at their highest point. Those are the two positions I'm being asked about. All right, so the givens are, I have the mass, okay, and I have the initial velocity. I also have the initial height. It's 0 meters, okay? I also have the final speed. How do I know what the final speed is?
It's the same as the initial speed, because, right, this one's going up, this one's down.
Oh, sorry, they're only asking about the highest point. You would be totally right. If they came back down, yes, the speeds would totally be equal. But they're asking how high will the child get? Okay, so in that case, VF is 0. At the highest point, VF is always 0. But you're right, if energy was conserved, totally be the same number, yeah. Okay, so VF is 0 because we're talking about the highest point. All right, so that means then that I can do this. Initial potential plus initial kinetic equals final potential plus final kinetic. Would you get marks for most of this work on a test? Okay, oftentimes, guys, these questions can be, like, a question like this would probably only be maybe 6 marks, but when you start getting a little more stuff into it, it can be upwards of 7 or 8. Okay, so you want to show all of your work. Okay, given the context of this question, okay, my initial height is 0. That means my initial potential energy is 0. My final velocity or speed is 0, so I don't have any final kinetic energy, and I'm back to kinetic equals potential. Right, so I'll have 1/2 mv initial squared equals mg h final. I'm looking for h final. What do I do to get it by itself? Divide by m times g, yeah. All right, so if I divide by m times g, and I bring that over here, because there's no pluses or minuses anywhere, the m's will cancel and go away. Okay, and I'll be left with 1/2 times 1.6 squared, that was the speed, okay, divided by 9.81. This kid's not getting very far off the trampoline, okay, they don't have a lot of energy. 0.5 times 1.6 squared, okay, it's only 1.28, divide that by 9.81, about like that, okay, you're getting 13 centimeters off of the trampoline. Okay, they didn't try very hard. Okay, that's what it comes out to. Everybody all right with that number? Okay. Every question we've done so far, same pattern? They're all going to be that way. Just like the work energy theorem problems had a pattern, conservation of energy problems have a pattern. Okay? All right, I'm going to give you about a 4-minute break here within the classroom, and then we're going to talk about a different context or a couple of different contexts here. Okay? Okay, so as you go down the hill, potential energy turns into kinetic. As you go back up the next hill, kinetic turns into potential, okay? And you're always flip-flopping between potential and kinetic. But what they add up to is always the same number, okay? So a roller coaster is an example of that. So is a kid on a sled, that's a toboggan, okay, going down a hill, right? They start out here. Okay, they've got, you know, an initial height, they've got an initial speed, okay, down here, they've got a final speed and a final height, but their energy is the same. The mechanical energy, I should specify, is the same. How much of it is kinetic is different, how much of it is potential is different, but they add up to that same number all the way down. Everybody all right with that idea? Okay, that's what we're going to be working on the rest of today, all day tomorrow. Okay, and part of the class on Thursdays. All these situations and being able to calculate. Here's the good news. It's just algebra. And you've already proven in the work energy theorem questions that you can do this level of algebra. You can move stuff around and solve for it. That's really all. The only trick here is identifying, is this a conservation of energy question or is it a work energy theorem question? Which is why I harped so hard on, does it have a force? Okay, is more than one kind of energy changing? That's how you identify or tell the difference between the two. Okay. All right, I want you guys to copy this question down, and then I'll give you a few minutes to try and solve it. But right now, I'll talk you through it. So this is a sled. right? I just showed you that, just told you sledding down a hill is an example of a context of conservation of energy. So at the top of the hill, the person is 30 vertical meters above the bottom of the hill, and they're moving at 1.5 meters per second. Okay? That should be 17, sorry. I gotta redo that. Actually, let me erase that number. Okay, a little while later, they're moving at 17.5 meters per second. How high from the bottom vertically are they now? Okay. See if you can solve that one. All the givens are there. You got to do a little bit of EI equals EF algebra here. Okay? But I think you guys can handle it. I'll give you a few minutes and then we'll go through it. Okay, so in this one here, our givens are that we know the initial speed. They're moving at 1.5 meters per second when they are starting this on the hill. Okay, we know that their initial height is 30 meters, right? And we know their final speed is 17.5 meters per second. What we're looking for is their final height. Okay, so if we're doing that, okay, we know right off that EI equals EF. Because this context is a conservation of energy question, there's no force, there's no mention of work, okay, their energy isn't changing between the top of the hill and this point on the hill. All right, now this is mechanical energy initial equals mechanical energy final. So we expand that out. These are the two things I add together to get initial mechanical. These are the two things I add together to get final mechanical. Okay. Previous to this question, we've been able to cancel some of those off because they're zero. Are any of them zero in this one? We have to assume that the final potential is not zero. They are asking us to calculate the final height. It's pretty rare that they would ask you to calculate for zero. Okay? So we have to assume that none of these are zero this time. What I'm looking for, final height, is part of that term. Agreed? Is it a good idea to get it by itself now before I put in all the formulas and have a whole bunch more numbers to put in? Okay, how do I get EPF by itself?
Subtract.
Right, subtract EKF over to the other side. All right, so what I'm going to have there then is the initial potential plus the initial kinetic, in other words, the mechanical energy anywhere down that hill, okay, minus the kinetic energy at the point in question. Okay, so if I go mechanical minus kinetic, I should get potential. All right, I'm looking for HF. HF's not even on the board yet. So now I have to put in all my formulas. Okay, potential energy, M times G times H initial, right? Kinetic energy, 1/2 mv initial squared. Final kinetic, 1/2 mv final squared. Equals M times G times H final. All right, at this point, you could leave M in, or you can cancel it off. Why? Is every term in that formula multiplied by M? Then the effect of M is the same on all the terms, agreed? That means M doesn't matter. I can cancel M mathematically, okay? Or you can look at it logically. All things fall at the same rate regardless of their mass. Doesn't matter what is sliding down that hill, it will go the same speed at that point, okay? I'm gonna leave M in because I'm sensing people like, I like this clear. You get the same answer if you leave it in, and you're given it in the question. Okay, so I want to get HF by itself. What do I have to do with the M and the G? Divide it over to the other side. All right, I've got HF isolated. Time to plug in my numbers. All right, the mass was 70 kilograms. All right, so we're going to have 70 times 9.81 times 30 meters, so my initial potential, plus 1/2 times 70 kilograms times 1.5 squared, my initial kinetic, minus 1/2 times 70 times 17.5 squared, my final kinetic, all divided by 70 times 9.81. Right, that's going to get me my final height. Okay, so 70 times 9.81 times 30 plus 0.5 times 70 times 1.5 squared minus 0.5 times 70 times 17.5 squared. All right, divide that by 70 times 9.81. Okay, so now we're at a height of 14.5 meters. We've come down just a little more than halfway, vertically speaking. All right, so 14.5 meters would be my final height. Now, I just want to demonstrate to you that if I don't put the mass in there, I get exactly the same number. Okay, so I put 70 in on every one of these. If I just go 9.81 times 30 plus 0.5 times 1.5 squared minus 0.5 times 17.5 squared, okay, and then I divide that by 9.81, I get exactly the same number. Mass cancels, you can take it out of there, or you can leave it in, okay? You will always be given it, however. Here's why. A few years back on the unit exam, I forgot to put the mass in the question. And I had people coming up to my desk. First person came up, Mr. Coderre, I think you forgot to put the mass in question 7. I'm like, oh yeah, I did. It was a roller coaster. I'm like, it's 250 kilograms. Going back to their desk. A little while later, another person came up and they're like, Mr. Coderre, what's the mass for number 7? And I couldn't remember what I told the first person. I gave him a different number, and all of a sudden a bunch of people in the class's eyes got like super wide and like, oh. And then I saw a few people smiling who were like, it doesn't matter. We can give him whatever number he wanted. And I was tempted to just start giving out different numbers for every person. But I got up and said, hey guys, I forgot to put the mass in. So you guys will know the mass will be there. Need it, don't need it, up to you. Okay? All right. Tomorrow, gonna work on some more like this. Thursday, a few more, talk about efficiency. Friday, unit exam review. Monday, unit exam. Coming right up. Okay, don't forget your work labs are due tomorrow, 8:30 a.m.